Okay. So how is my board? Is my board okay?
It is wonderful.
No, I mean the focus. Okay. So the last talk was without heuristic ideas. So today I'll make a combination of, I'll try to make a combination of heuristic ideas and mathematical formulas. So I hope that I'll show you two puzzles and some new technology. Okay. So and everything would be about the CPN sigma models. I will talk only about CPN sigma models. Okay, so the first thing that I'd like to say is the explanation why we had a ring. What is a linear functional? From topological quantum field theory point of view. Point two. In the same language, I'll explain you so-called Handel gluing operator. Handel gluing operator. I would say I will consider example in CPN model. And okay, I will not say about Landau-Ginzburg, but this technology could be applied to Landau-Ginzburg model too. And here I forgot. I forgot there'll be a puzzle. And I will provide some solutions. And some philosophy around this. About what? Not about the puzzle, not about the Handel gluing operator. Philosophy about solution. So even if you don't like philosophy, you will see the example, puzzle, and solution. Okay. So idea is to have philosophy only on the top of some knowledge, not before. Okay. Then I'll describe so-called descendants of observables. Four equal 3 to 1 puzzle. Of course, with solutions. You see, in the modern world, you should not puzzle people too much. In old days, in Soviet science, people were puzzled and they suffered. And then they came to solution. Now, world is much more smooth. So whenever puzzle appears, okay, you have to show the solution as soon as possible. So you see, these puzzles are just to attract your attention to the problem, not to make you think. Okay. And time number 4, I decided that I'll add a bit more information here. It will be equivariant cohomology, equivariant volumes, equivariant formulas. So it is kind of introduction into Givintany-Nekrasov. You see, I decided that when I explain to you what are holomorphic maps in such detail, you need to take advantage of the fact that you know it and get some information about this. Okay? So I decided that we should not miss this piece of knowledge. Right, Pasha?
Mm-hmm.
Well, why should we miss it? If it's that simple. Okay, so here we go. So this is our plan for today. And moreover, I will not hurry up, okay?
Mm-hmm.
So if I'll go too fast, so maybe Pasha will stop me, okay? According to advices of your father. So, about a ring. We have the worldsheet CP1. We have the target, say, CPN. We have points here, Z1, Zk. We put here observables, O0, O0 of Zk. And we would like to study the property of this correlation function. Of course, here we have holomorphic maps. So it is a sum of a degree. And that's what's left from the functional integral. Let me try to show you the ring structure that appears here. So let me be very simple. First of all, suppose I have only one point. So I can have an observable sitting at this point. Of course, the correlator. So what I'm telling you is heuristic. However, correlators could be studied directly from the formulas, from the description. O0 of Z1 is independent of Z1. So nothing depends on it. So this thing is some function that depends only on the type of observable. So we have a linear function. It takes the space of observables into complex numbers. Now, suppose that we have 2 points. K2, Z2. it turns out that this correlator is also independent on Z1, Z2. So the reason why I say that this correlator is independent on Z1 and this is independent on Z1, Z2 is heuristically energy momentum tensor is Q exact. So derivative with respect to Z1 is comes from the correlator of energy momentum tensor. Q applied to O is 0. Energy momentum tensor is exact. So this derivative is 0. So this is a heuristic argument that works in any topological theory. However, I showed you explicit formulas. So in explicit formulas, we can see how this heuristic argument is working. So what was this Z? Z1 was coefficient in the linear function in the hyperplane. Remember that we had a hyperplane. So there was A, and here was something like alphas, A's. Here we have Z1 to the power P, okay? Something like this. Anyway, all this is a hyperplane in CP D plus 1, N plus 1 minus 1. And different Z's correspond to different coefficients. It means that we were rotating hyperplane. And of course, intersection is independent of this rotation of the hyperplane. Okay, so this is a mathematical confirmation of this heuristic statement. This is a heuristic statement. This is a mathematical statement. So I could put in some indices. You see something like this. So this is the equation. Actually, there was a system of equations. But there are linear equations on A. Heuristic confirmed by the calculus. Okay? Now, similarly, I can show that this thing is independent on Z1, Z2.
Sorry, could you remind? So what's the relation of the hyperplane? Is it the description of O0?
So yes, this is a description of O0. So once again, in our particular model, O0 was corresponding to hyperplane intersecting O0 K1.
All right, hyperplane.
Was the intersection of hyperplanes K1 times.
Okay.
So equation for each hyperplane is like this. So would it be just for K1 equal to 1? I would have this condition, equation for the hyperplane. So this is an equation now for hyperplane in this space, in the space of maps. Because all this is a linear function on A's. And A's are homogeneous coordinates in the space of the quasi-maps.
Who are alphas?
Okay. Thank you, Pasha. Because so I need to remind that we considered the map that was Fi was AIP Z1 to the power P, Z0 to the power D minus P, sum over P.
Mm-hmm.
Okay. So this was a quasi-map.
Yes.
So these were coordinates on the worldsheet, homogeneous coordinates. So A's are also homogeneous coordinates on the space of quasi-maps.
Mm-hmm.
Now, what do I mean when I say observable one? It corresponds to hyperplane. I need to take the very definite hyperplane.
Okay. Yeah.
So hyperplane is determined by the vector alpha.
Yes. Yes. Mm-hmm.
So equation for hyperplane is this.
Mm-hmm.
So O1, and I would say, I would put it like this. I would not just say O1, I would say O1 alpha to show that it depends on alpha, not the class of some cohomology, representative.
Mm-hmm.
So representative corresponded to alpha I, AIP, Z1, Z1 to the P, Z0, D minus P. Sum over I, sum over P. So what is this? I would even take out brackets because it's misleading. Here it's just a product.
Mm-hmm.
For a given Z1, Z0, I consider this as a linear equation on A.
Mm-hmm.
So this is hyperplane in quasi-maps. Because it's linear in A.
Mm-hmm.
So what happens if I change some parameters? If I change alpha, it is the rotation of the hyperplane in the space of quasi-maps. If I change the ratio Z1 to Z0, it's also a rotation. By the way, if I rescale Z1 and Z0 simultaneously, it is the same hyperplane.
Mm-hmm.
Okay? So it is good to see observable explicitly.
Mm-hmm.
Because observable, O1 alpha is delta function here. I can put here epsilon. Then everything is as explicit as possible, right?
Yes, 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 yes.
Then, so Pasha, please stop me if I'm going so too fast. Because you would see puzzles and you can enjoy them only if you understand what is going on. Okay. Now,
So when you say delta function, it's somehow in the A variables.
so in A variables, yes.
Mm-hmm.
You may also consider it as a delta function in A and Z variables. But at the moment when these are fixed, it's delta function on A variable.
Mm-hmm.
Please take into account that this thing is linear in A and non-linear in Z.
Mm-hmm.
Okay. Now, what is O2? 0. O2 corresponds, I said, H times H. What does it mean, H times H? There is no such a representative as H. So if I can write down representative, it's much better than if I can write a class, right?
Mm-hmm.
So good representatives is something. So I put here alpha and alpha tilde. Okay.
Mm-hmm.
When I say corresponding, what do I mean exactly?
Which product of delta functions?
Product of delta functions.
Mm-hmm.
Alpha tilde. Everything is the same. I will not be lazy. I'll write it out explicitly. And you may say I can choose here epsilon, epsilon tilde. The integral will not depend on it. But I would like to write down this. So you would have the feeling that there is no mooking. There is no kidding, no cheating. Everything is explicitly. It is computation, not in so-called topological quantum field theory. This is a computation in calculus.
Mm-hmm.
It's a computation of Gaussian integrals. Okay? And you may play with this product, this differential form, on the space of A's, and see that when something changes, this differential form is changing by something exact. Exact where? Exact on the spaces, on the space of A's.
Mm-hmm.
Not on some mysterious space of holomorphic maps, etc. Since you have a representative, everything is under control. Okay.
But so let me see. So so we want a form on the space of quasi-maps, which is sort of a quotient of the space of A's, right? And it doesn't really descend to the quotient because of some scaling property. So if we scale all A's simultaneously by a factor,
it descends. It descends. Pasha, thank you for the question.
Mm-hmm.
Let us see it in this way. Let me put together alpha z into some omega
mm-hmm.
with a coefficient made out of this.
Mm-hmm.
And here we have A. And it has capital index that I'll call B. It's I and P together. So the formula is explicitly this. Sum over repeated indices is assumed.
Mm-hmm.
Okay, I can even write it down. I will not be lazy. and here. So this is different. So that's what I mean by differential form. Now let us see what happens, Pasha, as you say. What happens if we rescale? So differential form. So that's what you mean. The differential form itself would change. Yes?
Yes.
However, epsilon going to zero limit would not. So then you may ask, how should we integrate, right? In this case. So I would propose to integrate in the following way. I would propose to integrate not over the space of, I would propose, of course, to integrate over this space.
Without the quotient.
Yes, without the quotient. Get an explicit function. And then take a limit. But in order to do this, we need to put in, we need to take this differential form and multiply it by something. So the good thing is that this exponent is, of course, integrable on this bigger space. So what would you propose? How to integrate? Okay, so let us consider, Pasha, let us consider an example. Since you have equation, we can go into some details. Especially because this would be kind of important later on. You see, Pasha?
Yes.
So would your question disturb my general plan? I would tell you, it is a detail. We can just intersect delta function. However, I am concentrating on this because this issue, we would use this issue later on. I wanted to put it to the point number 4. It's called the Nekrasov-Gvintal calculus. However, since this question arises right now, it's a time to discuss it, right? Good. So let's do it. So let us. So the question is how are we integrating the classes, the smoothest classes of the delta forms? We actually would like to integrate. So it's a question how to integrate. Over CPM. Okay? So let us discuss this. How to integrate over CPM. Okay? In general. And this would be a particular example. So CPM is C m plus 1 over C star. we would like to consider differential forms on CPM. Okay? So differential forms on CPM are differential forms on CM+1 such that the Euler vector field that is the I don't know how to call it, YA, d over dya, sum A going from 0 to where? To M. So here is vector field. Such that LE omega equals to 0, E omega equals to 0. So these differential forms are differential forms. So here there is a projection. So such differential forms are nothing but the inverse image of omega. Okay, I'll put it like this. So I'll explain how to describe differential forms omega tilde that are P star of omega. So differential forms that are P star of omega are exactly these. They are formulas omega tilde invariant with respect to Euler vector field, horizontal with respect to the Euler vector field. Okay?
Mhm.
It is clear. And here I need to cut out 0. Now, suppose that I'm studying. Now I think I know that it is hard to integrate over CPM. Okay? I would prefer to integrate over C M+1. I would like to understand. Okay, I think I can erase it. I'll restore it later. I'm looking for the following formula. Omega L. I'm looking for the integral of CM+1 of something.
Mhm.
I'd like to get this formula.
Mhm.
So, bad guess would be to put here P star of omega 1,
Yeah.
P star omega L. It's a bad guess. You should not do it. Okay, but it's not very dangerous. If you do this, this is definitely 0.
Mhm.
Okay. So it's not only it's a bad guess, it's useless formula, because here the sum of dimensions of omega I from 1 to L, should be equal to 2n. Okay?
Mm-hmm.
And here, so here, the sum of dimensions is again 2m. But we would like to integrate over m plus 1 dimensional space. Okay?
Mm-hmm.
So, so what should we do?
Wedge it with something else that goes into the direction of the order rectangle.
Yes. So it is clear. So it is clear what we need. Here we definitely need some form that should be of dimension 2.
Mm-hmm.
And I am not telling you why, but I would like to call this. So there are several ways how to call it. You see, now I'm trying to choose the appropriate name for this form, and okay, let me call it like this at the moment, and then later maybe I'll rename them. So maybe I'd like to have 1, 0 and here 0, 1 form, such that I will get this formula. Here, let me make a twist in reasoning, okay?
Mm-hmm.
I can write down formulas, but let me invoke what we will call the quantum field theory intuition in writing this AA bar, okay? If you allow me to do this.
Mm-hmm.
And the intuition is gauge symmetry.
Mm-hmm. So should it be Faddeev-Popov formula?
Exactly. So let us play with this. So I would like to consider this p pi of omega 1 times pi star of omega L, consider like exponential of some action that is invariant. Because this is definitely invariant. This is invariant under LE and IE. So this thing may be considered as invariant action.
Mm-hmm.
And I would like to consider C star as a gauge group. So the fact that this gauge group is finite dimensional is not very important. Ideologically, it's a gauge group. And also, this is the simplest gauge group here. Moreover, this gauge group is a complex gauge group.
Mm-hmm.
Okay? So what should I do? Oh, I'm sorry. I'm sorry. Алло? Да? Да-да, вы знаете, мы еще сейчас думаем, в понедельник я вам звоню. Документы получили, все получили. Я вам написал. Okay. Gauge group. So C star is a gauge group, and actually it's not just C star that is acting here. It is C star 1, 1.
What does it mean?
It is because this is a generator of C star, even generator. And this is an odd generator. Okay? Now, let us recall quantum field theory procedure and then reinterpret it in this geometrical term. Okay? So the rule of Fadeev-Popov gauge fixing is point alpha. Consider BV extension of the action. So what would it mean to consider BV extension of the action? We need to take an action and add to it C. That is a ghost field. And here I need to add the vector field. Okay, maybe in this way I'll go too far with BV. So I'll be, see, it will take too long in such detail, but still. So I'll not do the very long way. I'll go shorter. So first we need to consider ghosts. So what would be ghosts? There will be C and C bar for the C star. Also, I need to take fermionic ghosts. So how should we call fermionic ghosts? So fermionic ghosts in superstrings are called gamma. Okay? So I will call them the same way, so it would help you understand the superstring notations. Okay? Gamma bar for this odd. Okay? Now, I need to, now I have to consider gauge fixing. Function. So gauge fixing function is something that people used to call F, okay? So the role of gauge fixing function, F, is such that the action of the Lie algebra on the gauge fixing function F with indices, I need to find the indices, I, is non-degenerate. Okay? So when I say non-degenerate, I call it N, and AI. Okay? And then on this Fadeev-Popov procedure, I do the following. I write the following terms. I introduce Lagrange multiplier, so Pasha, how should we call Lagrange multiplier?
Lambda.
So lambda, good, because of Lagrange. Lambda I. So then we write the following formula. So here, and sum over I is assumed. So we have this, and also we have, of course, ghosts. So Fadeev-Popov introduced two types of ghosts. However, here we have no choice. Here we know how to call them. CA, it's a so-called C ghost. C ghost. That was actually a Chevalier generator of 50s. Okay, but it is only C ghosts. But there is also a B ghost. Okay? BI, right? It is B ghost. And I need to say that Chevalier never had B ghost. Right? B ghost. Okay, introduced by Fadeev-Popov. You see, when I'm explaining this, I'm also able to correct the history. So this was old, this was new. So what actually was introduced by Fadeev-Popov was not the pair of ghosts. The new element was the B ghost. And now, so I put all terms here. Lagrange multiplier. And now I'm writing it like this. Plus I have this function. Fadeev-Popov procedure would be to study this integral. So it doesn't matter for me to write crazy d. D lambda, db, dc. Put in this one. Okay? And when I take the integral of a BC, I will have this thing, so-called Fadeev-Popov. Determinant.
But wait a second, we had more ghosts.
At the moment, I'm explaining bosonic piece of the story.
So we had the barred ghosts and the fermionic ones.
Sure.
But also even in the bosonic sector, there was also the barred part.
Yes, yes. But you see, before I'll write all this, okay, I just want to put it in the framework. So let us see the general picture. There was a problem, okay? So it is a silly school problem, how to integrate over CPM, how to integrate over CPM. But we need to address this problem scientifically, right? So we need to, we would like to think how in principle to integrate.
Do we have our favorite F?
Do we have our favorite action?
F, the gauge fixing.
We will come to it. We will come to it. At the moment, I am just recalling to people who doesn't know how physicists approach to this. Okay? And also, I need to say that physicists are not only writing this term, they are also putting epsilon term. You see, physicists like epsilon very much. Epsilon letter, I don't know why they like it so much. But
well, I had a professor in university who was saying that he likes epsilon small because it's small.
good. You know, it's a good point. Physicists like this epsilon because this epsilon is actually a coupling constant. And if there is no coupling constant, physicists feel that they're not doing physics. When you say that coupling constant is zero, for physicists, it's just out of, they got crazy. Because it doesn't sound nice for physicists that something is exactly zero. Physicists would like to say that there is a coupling constant that is small, but very small. Yes, exactly. It's a reason. By the way, in the same way, physicists do not like delta functions because delta functions is not a function. That's why, as always, they would like to smooth it with some epsilon. Yes. So thank you, Pasha. You explained to me why physicists are doing this.
No, actually, because it looks small in the blackboard. That's why. Small in the sense it looks small in the blackboard.
You see, this epsilon looks small in my mind.
Yes.
And you see, I don't care about the blackboard. I care in my mind. So when I have this epsilon, you see, I imagine something that is universally small. Universally small. Okay. So that's what physicists are studying. And at the end of the day, they study something like So there are two options. You can either integrate over lambda or keep it like this. So in any case, you have quadratic expression everywhere here. So it's an idea. And if you have any problem with the gauge group, you see, so it means that something is invariant with respect to this gauge group. So you come to this zero section at the zero of f. So this is a physicist's idea. Okay. Now, let me follow this path. Okay. So people say that if you do this, you have the integral over the delta function of f of fi, yes?
Mm-hmm. Mm-hmm.
See, it's not good to say that it's delta function, because only the full object is invariant. I want to restore the indices. So what happens if I will rescale this? Not by lambda, but by mu. I just want to see that nothing happens. If I rescale this, I have mu in front of lambda. Still, this n is not independent of f. Once again, this n is LVA Fi. So I rescale here, I rescale here. The rescaling of f, of curly f, could be absorbed in rescaling of lambda I going to mu lambda I, bi going to mu bi. Okay? And it would cancel from this measure. Okay?
Mm-hmm.
Interesting.
Mm-hmm.
So that's why we need this term. Okay? We can generalize. What would happen if I replace Fi by some mu ij Fj? You will, of course, have similar rescaling of lambdas. And here, the determinants of mu would cancel. Okay?
Mm-hmm.
So here, in this formula, without using the B-heuristic or homology, etc., I show you that this is a good choice.
Mm-hmm.
So now, let me tell you something. So this is the gauge fixing. And let me tell you something. At this moment, I will follow the person who always occupies my mind, named Edward Witten. Okay? So one of the paths that he says is, let us concentrate on the odd part of C star 1, 1. Okay? Because in his works, he always concentrates on the odd part of C11. Okay? So let us follow his advice and concentrate on the odd part. And then we will see what is the geometrical meaning. Edward Witten. And what does it mean? So let us follow him. So, in this case, we would definitely see that these ghosts would be what? Fermions. These would be fermions. Oh, sorry, these would be bosons. What I'm saying. These would be bosons.
Mhm.
And here, and these would also be bosons. Okay? So what would they mean here by non-degeneracy? I would mean the following. I have the gauge transformation that takes d phi tilde into what? Unfortunately, I already used this lambda, mu rho d phi tilde. No, this is bosonic. So fermionic transformation. It's a contraction of the Euler vector field. So it is what? It means that I take derivative with respect to d phi tilde a. And I multiply by phi tilde a. Okay? Pasha, is it clear?
Yes.
So this is the gauge algebra that I'd like to fix.
Yes. D is missing.
Okay. So now I'm looking for what? I'm looking for the gauge fixing function f.
I know. That's good.
So since I have to differentiate with respect to d phi tilde, okay, this thing should depend on d phi tilde. So it means that this function should be function of what? Of this. And let me take a linear function. Because it's good enough. Okay? Now, what about this n matrix? What can I say about it? N matrix is phi tilde a d over d d phi tilde a applied to f tilde. Okay, you use zero index b. So can I compute it? Yes, of course. This is phi tilde A okay. So I need to take such f tilde that it is not degenerate. Mhm. So how can I do it? So the simplest way is to have here something something positive and quadratic, right? Hmm? I want this to be so. For example, I can take fi tilde of phi tilde. What? Phi bar A. Okay. You see, here I have an index downstairs. Here I have an index upstairs. As and the Moscow Physical Technical Institute, we never had such a thing. So here I have a constant metric. So similarly, you see, I wrote you the holomorphic piece of the gauge symmetry. Similarly, I have an anti-holomorphic piece of the gauge symmetry. Okay. Because a complex group, or I can write it down this way. It would not really matter. I can do it like this. Okay. Now, what I do then? I will write an action. Okay. So after I found this f, oh, by the way, do I have enough of these guys? Yes, I have enough of these guys. I'm sorry. Maybe I made a mistake. So here I need. I'm sorry. I guess I made a small mistake. You see, we need to have this determinant. Okay, maybe not a mistake, a comment. And comment is that here I have two indices, one index here and one index here. In the case under consideration, this A takes value 1, and this takes value 1. Okay, so just comment that A equals to 1 and I equals to 1. And also, unfortunately, this A is not that A, because there is only one Euler field. Nevertheless, I can write down what's going on here. So here I have gamma and beta. And let me compute n. So n right now is a number. So n is what? phi bar B, eta B bar A, phi A. Okay? Okay, everything has tildes. So this is M. Once again, this was F tilde, and this is M. Now, now I am coming here, and I'm going to rewrite this term in our particular example. So, I would like to write exponent of what? Of I. So this lambda was Lagrange multiplier. Now I need to write down something. It was bosonic. Now it has to be fermionic. I will put here F, okay? To stress that it's fermionic. Here I'd like to put F tilde. That is F tilde B phi tilde D phi tilde B. Okay? That I would immediately rewrite as A. As what? As phi bar B eta B bar A D phi A. Okay? So this is my choice. Here is my lambda. Plus, I'll have gamma. Phi bar tilde B at B bar A. Phi tilde A. And here I have beta. That's it. And now I'd like to take epsilon to 0, because I do not need these quadratic fermionic terms, okay? Because this epsilon is in front of, it would be in front of quadratic terms in Grassmannian variables. I do not need it. Grassmannian delta function is good enough.
Sorry, I
And
have a
here I have
question.
this B star of omega.
Andrei, there's a question.
Yes?
So the gamma and the beta, they are bosonic or fermionic?
Bosonic.
Okay, thank you.
They are bosonic. Because we are considering the odd piece. So that's what we have. Now,
So that looks, I mean, scary. That doesn't look at all like a Gaussian integral or anything.
it looks,
Well, there are quite fourth order terms in fields. Third and fourth order terms.
still you can compute it. You see, it is good to scare somebody. You know, in modern world, you not need not only to puzzle somebody, you need also to scare him. Okay? It's because what we are going to do now. We are going to take this integral. So now let us see what are the good news here and what are the bad news here. Okay? Moreover, Pasha, your scare equation has a reason.
No, I see that it's quadratic in sort of in the auxiliary variables that we introduced, and that's what we are going to integrate out and obtain our sort of integration on the quotient space.
And you see, because what we are afraid of, that when we integrate over beta and gamma, we will get this term where? In denominator.
Right, that would be unpleasant.
Okay? But it's exactly, but we had to expect this problem. And do you know why we had to expect this problem? We had to expect this problem because we tried to go to see n+1 over C star.
Yes, yes.
And actually, we need to subtract zeros here.
Yeah.
So we actually have a chance to have this term invertible. So it means that here we have a problematic region. Now, now let me make further comment. The further comment that I'm going to do is, you see, I will make several comments. Actually, I wanted you to see this because this is a prototype of many constructions in quantum field theory. In particular, it's a prototype of the scalar fields in n=2 super Young wheels. I mean, what's going on? So actually, you see, we have this beta gamma term. We have this thing in denominator. Okay? Now let us see. How do we understand this term? So this term is what? It is so-called unnormalized connection. You may ask, why do I call this connection? This is the one form. Now it's time to look. This is the one form. Okay? And what we actually wanted to construct, we actually wanted to construct a one form such that contraction of the Euler field with this one form is non-degenerate. Okay, so that's what we were looking for. Okay, in the textbooks, you say that equation for connection is
I see.
AB is delta AB. So that's what you see in the textbook. And here we have contraction of the vector field with the one form should be non-degenerate. So I'll call this normalized. So connection that is normalized is, of course, connection that is not normalized. I will call A divided by N.
So the unnormalized connection is the whole exponential or the integrated exponential.
So this term is unnormalized connection. The beta gamma integral is a normalization of the connection.
Oh, I see.
Okay? So here we actually so it means that here we after we write it this way, we actually have a branching point. And this branching point is, what should we do? Is it possible to normalize connection? Or it is not possible to normalize connection? Are we allowed to divide by such expression or not? The ability to divide by such expression would mean, in general, so in finite dimensional case, you can always do this. But then, Pasha, look what you said. Would we consider F being F divided by N would we do it this way? Everything would be fine. We will not get this determinant. We will not get this factor. However, in this way, we have to put it in the action. Okay? So in quantum field theory, the analog of this N term is even more harsh than this. The analog of this N term is some Laplacian. And actually, we will see there are these fourth order terms. And we will see these fourth order terms in supersymmetric Young-Mills theory when we will come to it. Okay, so there are these terms. However, when we speak about particular example in finite dimensions, we are not afraid. Or later on, maybe we would like to find some technique to replace this by something more tractable. Okay? So let me summarize the answer to the question we started. How to write down remember that we started from the equation, yes? So it's an integral over Cm plus 1 of P star of omega 1 wedge P star on omega t. E to what? To what I will call unnormalized connection times lambda. Lambda fermionic. I'm sorry, I need to add more things in the integral. Over C m plus 1. Actually, without 0. And what I have here, integral d lambda, d beta, d gamma, d lambda fermion, a fermion plus beta, gamma, I, E, A. So here, so no, that here, so what I did here, here I fixed the odd degrees of freedom, okay? However, I also need to fix even degrees of freedom, okay? And concerning even degrees of freedom, I can use more standard way, okay? So now, for even degrees of freedom, I need another gauge fixing function, okay? So this, another gauge fixing function, would be what? I want E applied to something that would be non-zero. So here, the gauge fixing function could be just 5 bar 5 with another metric. It'll be good enough. And I will have BC system. So I'll put here the following thing to do. D lambda, DB, DC, E. Now I'll have lambda. Metric at a tilde applied here. Plus, I can have BC system. And here I need to apply Euler's field here. And here it's something like 2. So it is, so this is the procedure. Okay? And here I put epsilon lambda squared. And all this is an exponent. So that's what I have to do. Now we will have a 7 minutes break, okay? Okay. Okay, Pasha.
Uh-huh. Uh-huh.
So, so let me proceed as follows. Would I do things like this, like I explained? I could get all formulas, and also I have a possibility to cancel bosonic determinant by fermionic determinant. So now, you see, so at the moment, I try to explain you what is going on if I consider even piece of the gauge group and odd piece of the gauge group separately.
Mhm.
Okay? And you see that formulas are not that easy. Okay? In particular, I had this I had this m in the denominator.
Yeah.
So it would mean that probably I would not get nice formulas for general forms, omega 1, omega k. So I could construct this integral, but probably I would not get nice formulas. Okay? But now I can use the fact that my system is special. There is a supersymmetry between bosonic and fermionic piece of the group that is acting.
Mm-hmm.
And this supersymmetry, in principle, may allow me to cancel these determinants.
Mm-hmm.
So I can still proceed as follows. However, there is a better way to see this cancellation. And the better way to see this cancellation would be to do the following. Would be to go to so-called equivariant cohomology.
Mm-hmm.
Because as you see, this looks a bit complicated, right?
Yeah.
And however, this possibility of cancellation, you see, if I do it like this cancellation would appear at the very last stage.
Mm-hmm.
So what I'd like to do, I would like to say the following. Let me consider only closed forms omega 1, omega k. Okay? So I need to say it explicitly. Consider what? That I have Q operator. That was QBRST. Okay? And QBRST was what? Let me write it like this. You see, unfortunately, index, I will write it like this. CLV plus gamma IV. What are the other differentials that I have here? I have Q DRAM.
So V is epsilon, the Euler vector field.
Yes. I have Q DRAM. And Q DRAM is what? It's D. And we say that it takes phi tilde to D phi tilde. Phi tilde bar goes to D phi tilde bar. So physicists prefer to write here not this, but psi bar. And here psi tilde. Here psi tilde bar. There is another Q that I have here. And this Q is related to the fact that I have the superalgebra. So, and this Q, I don't know how to call it. Let me call it superalgebra Q. So this superalgebra Q takes C into gamma.
Is that a value model for equivariant cohomology? Seems like-
Yes, yes.
Okay.
So now I'm saying that I can use the Weil model for equivariant cohomology. However, I am explaining why I'm doing this. So here, since I started to write things in the field manner, so the RAM would be psi d over d phi. Okay, sorry for tildes, but I started to write it in tildes. I can even write it this way, in explicit form. So I have complex algebra. So, so what I'm going to do, I'm going to write down the differential that is kind of a sum of this differential. So let me check that Q superalgebra anti-commutes with QBRST. So to see it, I can just show that it is because QBRST is gamma d over dc applied to what? Applied to C IV.
So there are
Okay.
some more terms in QBRST, right, with psi's.
Sorry?
There are some more terms in QBRST, right, with psi's.
Yes, so you see, yes, you are right. So that's so I have not. So QBRST is this plus this. 1 second.
Yeah.
Okay.
Right.
So it is C V d over d phi plus gamma V d over d psi. So here I consider all phi's.
No, sorry. Even in the Lie derivatives, there is a term with psi's. No, I mean the derivative acts on differential forms.
Right. You are right. So yes. So here is dv over d. So what would be the best way to write it? Maybe without writing it as components, but just
That's fine without components. It's clear what's going on.
so, otherwise it should be too long.
Yeah.
So this is C D I V plus gamma IV. Okay. We also have D, and we also have gamma d over dc. So what would be the best way to show that everything comes together? So the best way to show that everything comes together would be, so here dx here. You see, I don't want to have too many terms. I just want to show that this is d plus what? Plus q super algebra applied to what? Applied to CIV. Okay. So here I have the RAM. And here I have Q super algebra. So altogether, I can consider this as a D on the superspace. Right? On the super manifold. That is original manifold times Lie derivative, and I also put this. You see, if it's too complicated, you can look here for explicit formula. So D plus Q super algebra applied to CIV. So.
Sorry, X times what? P of what?
So X times P of Lie algebra. So Lie algebra is shifted by 1. And I have PT applied here. So coordinates here are just like phi's and c's.
Mhm.
So coordinates here are psi's and gammas.
Mhm.
Okay, so so I see that the total differential. So the total differential that I'd like to consider is universal de Rham plus this. So now the role of all fields is clear. Okay. Okay, it takes a bit longer than I expected. Maybe that's why I'm a bit nervous. But still, it's an important construction.
Mhm.
Okay?
Mhm.
Now, we see that this differential squares to 0. Okay? It's because it's of the form some q tilde plus q tilde some. I'm looking for the letter. But I have not used some sigma. Okay. You may call it Witten's differential, like this. Okay. Differential plus differential like this plus this anti-commutator. By the way, please see that this is bosonic. So this contains fermion number 1, and this contains fermion number 1. So it means that now I have this differential that I'd like to call Q total. Okay? And with the help, so you see this Q total joins together two types of differential. It joins together B with P differential for the superalgebra and the Rham differential. You see, before we used to think that Chevalier differential or B with P differential is something fundamental. Now we see that this differential is, so everything is written here. Is in some sense exact. So, I have an integration theory here that is not quite simple, right? At the moment. It is doable. But as Pasha said, you have something in the denominator. And here we can have something in numerator. So we will have to see some strange cancellation. So maybe it's not the way how we would like to proceed. We can't proceed by this, but it's better to study Q total, because if Q of omega I is 0, oh sorry, then I star of omega I is closed under Q total. It's because Q total consists of Y. First, omega I is independent on gamma, on beta. So I called it beta
On C.
on ghosts, on all ghosts.
Yes.
So second, omega I is declosed. Third, LV omega, and that's why I need to say, so I'm talking about P star, sorry. D applied to P star omega I equals to P star D omega I equals to 0. Okay? You see, I need to make one line computation because I'm saying that P star is independent. I am studying that P star is closed. Okay? Third, LV applied to P star is 0, and IV applied to P star is 0. So these P stars are special representatives of the total cohomology. Okay?
Mhm.
Now, I would like to modify integration theory that I constructed in such a way that I would not need to consider now. Modify integration theory in such a way that I could take f tilde to 0. You see my plan? So after I define something, then I can change representative such that the integral would still exist. And I could take f tilde to 0. Okay? So this is my plan. So I have to modify the total integral somehow. It means, so what is a tricky way to do it? The tricky way to do it is to regroup the total differential as d plus gamma d over dc plus this one. So it is split off. And pick up, you see, so I put it all together, and then I'm going to decompose it into pieces in another way, okay? I will take together this piece and this piece. And then I will separate everything into two steps. Step one. Computation of plus gamma IV homology. And then there will be step two.
Andrei, the board is out of focus.
Okay.
Okay, now it is in focus.
It is in focus.
Well, when you approached the camera, it became in focus.
Strange. Okay. And step two would be integration over gamma. So, remarks. I need to make immediately remarks. It is, why do I think that D plus gamma IV is a differential? Second, okay, so it's maybe the first thing to do. So so I'll proceed to this construction doing the following things. I would like to decompose. So it's one of the approaches. I would like to decompose C star as R times U1. So actually, C star equals to R positive times V1. Okay, but maybe it's better to write it this way. It's a C star. So this thing is acting as a dilatation, and this thing is acting as a rotation. Okay? So first, I'll treat the U1 part. So, just imagine that I was studying not Cm plus 1, but Cm plus 1 minus 0. So it means, it doesn't matter. So you see, U1 is a compact group. So I can choose everything to be U1 invariant. Okay? So now let us see how reasonable it is. And it is reasonable. So here U1 is finite dimensional and not only compact but finite dimensional. So here we can do it without any precautions. Because when I said d plus gamma IV square is not 0, it's gamma LV. So here I need to, to consider this as a differential, I want this to be 0. So what would this mean? It would mean that I will work on C m plus 1 with U1 invariant object. So would it mean that I work with C 2m plus 1? Warning, of course not. Because this object would be only U1 invariant and not necessarily, sorry, when I factorize by U1. So only invariant. I would like to say not necessarily horizontal. And this would be important. So I'll study this thing first. Then I'll go to this cohomology. And this will be the first step. And on the second step, I'll perform the gamma C, if you wish, integration. However, you may ask what kind of integration I would like to perform. So after I compute this cohomology, I will be left with what? With functions of gamma and C. And we will see how they will work out. Once again, I derived this because this would work in. So what are other models? It will work in sigma models, 4-dimensional super Yang-Mills. So these would be more complicated example of the same technology. Okay. So let me proceed with step one. And in order to proceed with step one, let me consider an example. And this example would be compute equivariant cohomology of C. Okay, it's the same. Okay, C to the power m plus 1. So how can I do it? Idea. Suppose omega is an integrable representative of D plus gamma IV cohomology on C m plus 1. So the integrand that we want to study, of course, consists of integrable representations because it contains exponents that fall at infinity. Okay. So now we will take omega as an integrable representation. So if it's an integrable representation, then we may study what? We may study the integral of this omega. Okay. In order to understand what this integral could be. By the way, it is clear that since D plus gamma IV is a first order differential operator, here we have differentiation, here we have differentiation. There is a multiplication. On cohomology. Okay. And I would like to do with the equivariant cohomology exactly the same thing as I did with observables in sigma model, namely, and consider omega 1, omega k. I would like to understand this thing. And here I can do the localization trick. Namely, I have multiplied by D plus gamma I U1 apply to something. And here I will put a parameter Let me call it T. And I would like to compute this guy. And the way how I will do it is the following. I will take as a star. Oh, star, okay. Out of letters. R. I will take as R the following thing. Phi.
What do you mean v of 1? What does it mean of 1?
What?
What does it mean v of 1?
Sorry?
What does it mean v of 1?
U1. It means that here.
Ah,
is
u1,
version of
sorry. Sorry, u1, okay.
Maybe I should say that U1 is, of course, phi I over d phi I minus phi I bar
Mhm.
d over d phi I bar. Tildes everywhere. So I'd like to put here some R, and then I'd like to have integrable representative for all t. And then limit t equals to 0 would be original thing, and limit t goes to infinity would be the localization trick that I'd like to have. Okay. So what I would like to take here, I'd like to take for R the following thing. Here I need to see plus or minus. I think also minus. No, this would give me 0. Actually, so I'll put bar here. So bar here, no bar here, and here I'll have phi I without bar d phi bar a. You see, tildes are. I'd like to take something like this. So let me see what would happen. What would happen if I apply this U1 to this object? I will get the following. From D, applying D to R would bring me e to the minus t d phi bar d phi a, sum over a. When I will apply U1, I will get minus t phi a, phi bar a, of course sum over a, no square. So this would be the exponent, and here I have gamma. So it's just this simple computation if I didn't create a sinus state. So these are is of course a one form. When I apply U1 here, I get a two form, and when I get a function, and when I apply the RAM, I get a two form. So this would be the two form, and this would be the function. And then what would happen if I take an integral? If I will take an integral, here, I will get the following. In the limit t equals to infinity, I will get an interesting formula. 1 over gamma m plus 1. Okay? And here, I will get omega 1 at 0, omega k at 0. So what does it mean? It means that from the full form omega 1, zero part of the form omega 1 and evaluate it at 0. And this is the integral. Now, do you see this sign? Gamma m plus 1. It's exactly the same denominator that we had in cohomology of the CPM. And this is not a coincidence. Moreover, I can do it even differently. I could take different gammas here. Generalization.
Sorry, what did you say about the denominator?
So I computed it, I got this.
Yes.
Why did I got this? Because here I have a Gaussian integral.
Yes.
In the limit t equals to infinity, everything is localized at 0.
Yes.
So here I need to take the m plus first power of t out to have a measure.
Yes.
So would I like to take differential forms out of these omegas? I would have power of t that is not high enough. And this would vanish. So bosonic integral actually gives t to the m plus 1, gamma to the m plus 1. You see, they come together. In numerator, I need to take t to the m plus 1 out of these two forms. So I get this plus, how to say, O 1 over t terms. So since answer is independent on t, I conclude that these terms are zero. So I got formula that looks pretty similar to the formula that we discussed last time. You see the same gamma m plus 1. Now you understand this gamma as the super ghost, as a gamma ghost for the total U1. Okay? Super goes for the total U1. Here you have 0. Remember that in the full story, I had to integrate over gamma. So integration over gamma, it would be something that I'll explain next time. At the moment, I computed this cohomology formula. So I was not able to fulfill the topic that I wanted. Okay? So I'll do it next time. I'm sorry.
Oh, sorry for distracting you from your course.
No, but I thought it was the time to explain this.
Mhm.
Because let me tell you what. Let me tell you that it is possible to modify the full theory. To modify this D, go to D plus gamma. How did I call them? A's. I, V, A's. Okay, where A is going from 0 to M. And do everything similar. And then the integral would be just 1 over gamma 0, gamma M. Omega 1 at 0, omega k at 0. This would be the integral. And it is reasonable to do the following. We may consider gamma, how do I call them? Gamma A as a sum over gamma plus gamma A tilde. So this would be integration. This would be what I will be integrated over. And this would be external background. And in this case, we will study not CPM, but CPM equivariant. Okay? Equivariant with respect to the action of the U1 group on the target space. And this would be equivariant generalization of the sigma model. Where these gamma A's would be considered as external parameters. And these gamma A's were first introduced by Giventhal in sigma model and Nekrasov gauge theory. So here maybe I'd like to criticize my friend Nikita Nekrasov, because when he is explaining this topic, he always goes directly to the gauge theory, because it's the subject of his main interest. However, my point of view is that you cannot understand the gauge theory before you understand signal models. And also you cannot understand signal models in this approach before you understand the covariance science. Okay? So the goal, final goal is here, but we have to go through this way. So that's why we do it in the following form. We studied something interesting, like quantum cohomology, okay? And then we found some formula with this denominator and this residue, and we found that there is phenomena, okay, of mirror, etc. And it means that we would like to understand more. And the covariant cohomology technology is something that helps you to get this understanding, okay? So would it be a standard course in mathematics, you know, like a 2 semester long? I should study with a covariant cohomology. But then we will not see where we are going for, where it is good for, and how something like this is important. That's why I changed the presentation. I explained a bit of physics, okay? Or a bit of mathematical physics. We found something about quantum cohomology, Gromov-Witten, etc., integrable systems. And then we understand that we need to deepen our understanding. And that's why it is the time for covariant cohomology. I actually wanted to do it like 1 hour later, but Pasha somehow forced me to do it, to start to explain it right now.
All right.
And maybe it's good. Maybe it's good. Actually, it doesn't matter so much when do we start a covariant science. But of course we have to start it here or there. Okay, it started here. You see, it's like a birth of child. Okay, it doesn't matter if you give rise to a child after actually 8 months and 3 weeks or 9 months. It doesn't matter. Child is already there. Okay. So somehow Pasha frightened me, and I started to give birth to a child. That is a covariant science. A covariant science, say, 1 week before it's expected. I just want to say that it is as healthy as another way. Okay.
Right.
Still, I'd like to summarize, yes, that I actually try to formulate several ideas, okay, trying to confirm them by formulas that we would like to go to the big space. So when we have a factor, we would like to go to the big space and lift differential forms to the big space. Okay? Because we can compute there. And then there is a problem, that when we leave differential forms, it seems that the dimension of space that we are going to integrate is bigger. This seems to be a problem. However, we may understand this problem as a problem of having odd symmetry that we need to gauge. And here we started to do this, gauging of the odd symmetry. And we found several phenomena. First phenomena that we found is that we needed normalized and unnormalized connections. Okay, so we met them. So what we used to call connection turns out to be just the gauge fixing in this for this odd symmetry. Okay, and this would be, of course, important later on when we will go to Donaldson invariance. But here we meet it for the first time. And if this is new thing, you should know it. We understand that normalization of connection, the thing that we are passing in the textbook, is actually the beta gamma integral. In this model and later on in field theory. Okay, we also realized that if we would like to integrate not anything, but something very special, namely the pullbacks of the closed forms, okay, it is better to combine all differentials together and have this four-term structure, and then rearrange terms in the equivariant differential and the rest. And that's why we start to do equivariant stuff, and at the moment it's only an observation. We found a formula that looks similar, but not exactly the formula that we had last time. We have this gamma to the n+1. We have this omega evaluated at 0. Still, we do not have an integral. So we found this. And also we found, after all these preliminaries, that it's possible to deform the theory, namely to consider to deform the Deram equivariantly. Why we should deform it? One way it is clear, because we want to go to CPM. But still, one would prefer, one would like to keep other gammas alive, and this expands the background. So basically, that's what I explained today.
Thank you.
Okay, and then there is a Chinese break. Okay. So because of the Chinese, not Chinese, it's an Eastern break. It's called the New Year. The New Year in the East starts at 9th, as Professor Sanhu told me. So that's why we will have a break in the seminars under the Chinese and Eastern leadership. Okay.
So there will be, will there be a lecture on next Wednesday?
No, because Wednesday is the
10th.
So it's Wednesday, so it's beyond the scope. So it would mean that there will not be official lectures.
Okay.
However, there will be Pasha, but we should not stop. There will be lectures that are only for Europeans, as you know.
Well, I'm not sure that I would be able to come to the lecture because my teaching started, so I'm not sure that I can get up at 2 a.m. and
okay. So it means that now we have a 2-week stop. So I will have a talk on Friday that I promised. Okay, and it will be recorded. So Friday would be the last talk of this semester because we have an Eastern semester.
Mhm.
Okay?
And so then the course resumes when?
Then the course resumes approximately, I need to check when will be the next working day.
Mhm.
Approximately in 2 weeks.
So around 17th.
Mm,
days
I
for-
need to check.
Okay, okay.
I need to check with I need to check with the Eastern participants.
Right.
So of course, there will be no course during the Eastern New Year.
But
It's impossible.
but
So people should drink, spend time with their families, you know.
but okay. Okay. Of course. All right. Thank you. Thank you.
Thank you very much.
Okay.
So I'll stop the recording then.
Right. Me too. Yeah.
Mhm.
Thanks. Bye.
Okay. Goodbye.
Bye.